All right, welcome to Spring 2014 final walkthrough. I'm James, and Raymond and I will be going through it. I highly recommend to do the problems yourself before watching this video. So let's start with what would Python print. It's really useful to sort of draw a little environment diagram on the side. So let's get started. Let's call this global. We have a f0 that points to a function f0, parent equals global. We have a f1, oh wait, not yet. So we have a h1 and h2 that are calling f0 with 3. So let's make another frame, call that f1 frame with our function call of f0. We remember to bind our formal parameters, so x gets bound to 3, f1 gets bound to a function f1, parent equals capital F1, f2 gets bound to a function f2, parent is still f1. And then our return values. So an interesting thing with Python when you return two values is you actually return a tuple that contains both values. So the 0th element points there, the first element points there. So h1 now points to the 0th element of our tuple. h2 points to the first element of our tuple. Okay, then we have a g0 points to a function g0, parent equals global. We have x is 14. We have an h0 that points to a function h0, parent equals global. And then we have a k0, points to function k0. I apologize, it's a little chaotic, but yeah, it'll make sense later on. So we have a h1 function call, h1. I guess we can keep labeling our frames, so it doesn't really matter. But h1, remember to bind our formal parameters as well. So h1, let's look where h1 is. It's not in this frame, it's in our global frame. h1 points to this function f1. f1 has a y. y is going to be 5. Let's run through the f1 code. X equals y, so x is now 5. And then our return value is x, which is 5 and 5. All right, let's go to our h2 call, h2, f3. We look through our parent, h2, points here, function f2. So f2 just returns x. So actually, we didn't even need to create this frame. I guess we'll save some room because all this function's doing is returning x right here. So we look at parent equals f1. The only important thing that it's in our f1 frame. So parent equals f1, x is 3. So h2 is 3. Now let's go to g0. So g0 is in our global frame as well. And so basically now the important thing to remember is our parent is global in our case. So when we look for x right here, we're actually going to look right here. X is 14. All right, so let's do k0 now. f3, well, f4, whatever. k0, remember to bind your formal parameters. G points to g0. So let's draw a little arrow to g0. A is 21. Now let's run through our k0. So k0, global x. So that means, so it says right here that is the same as non-local, but now we can modify global. So we look at our global frame, we find an x, we actually modify it instead of, so this line right here, instead of making a new x, we modify it. And then return value is going to be g with no parameters, so g0 with no parameters. We go to our global frame with no parameters, return x. But now x got changed, so it's actually 21. So let's do the, oh, this arrow is getting a little in the way. So let's do the same thing for h0. h0, parent is, global. Remember to bind our formal parameters. G is g0. So I'm just going to attach that to our arrow. And then A is 31. And then remember there is no, oh sorry, this is actually n. n is 31. So there is no global x call. So x actually is going to be a new variable. So we're right here, this line right here, x is now going to be 31 here. And then we're going to, our return value is going to be g with no parentheses, or with 2 parentheses. So g points to g0 with 2 parentheses, but the parent is still global. So our return value is still going to be 21 because the x is going to be looked through our parent frame. All right, so let's make a k0 call. k0 again. bind the formal parameters. G points to a lambda, where the parent is actually this frame. I'll just draw an arrow because I don't know what our frame number is anymore. And then our A, I believe, and K0 is going to point to G0. So let's draw a little arrow back to our G0. And then now let's walk through our K0 global X. Remember, again, now we're going to be modifying the X right here. Cross the 21 out. It becomes A. So A points to G0. So now X actually points to G0 as well. So then now we go to our return value. Return value is going to call G, which is this lambda, with no arguments. So we call our lambda. We go here now. It actually calls X with parentheses. So we look for an X. Oh, this parent is global. So we look for an X. It's not in this frame. So we look into the global frame. There is an X. So we call that X with two parentheses, which we'll call this function. Then we will return X, which going up through the global frame is actually a function. So what was tricky about this problem was that we actually reassigned X to be pointing to this function that's going to be returning X. So it's almost sort of like a recursive thing. So that is question 1. All right, so let's move on to 1b. This is a stream question in Python. Let's just review streams in Python. Remember, streams in Python and in Scheme are like linked lists where they have a first and a rest, but the rest is only evaluated when we need to evaluate it. And we'll see that that actually helps us quite a lot later. So remember, our stream constructor takes in a value, which remember can also be a stream, just like how linked list, the first can be a link. And then the rest, remember, is a function. This is important because remember, in linked lists, the rest has to be a link, but not quite in stream. So this could either be a lambda, or it could be a def compute rest. We've seen that in homework and whatnot. So let's take a look at the code. We have a const stream that takes in a value. Result equals stream. Our first is n, and the lambda is actually going to return itself. So just judging by this code, all we're doing is just making a stream with n. So every element is n. All right, let's look at make integer stream. Let's look down here. We have a make integer stream k starting at 1. And then the first elements across the stream are 1, 2, 3, 4, ... All right, now we can actually get to the problem. So that reading, we have to find the first 3 elements of C. So let's write out, well, we know the first element is 1 as the 1 appears there. So let's actually write out the lambda function. So our lambda is going to be, and then I'm going to abbreviate combined stream as C underscore S because I'm going to be writing that a lot. So yeah, it takes in an add, takes in a CS with mul C pos ints, and then it takes in a const stream, const S with 2. There we go. So what's going to be really useful is actually finding the values of these 2 streams to find the value of our entire stream. And let's look down here at combined stream. So combined stream actually first takes the 0th index and then applies fn, and then takes the first index and then applies fn. So all we have to do to find our first element is find our 0th elements of these 2 streams, then apply our function to it, and then find the first element of these 2 streams, then apply our function to it. So let's make a little table out. So let's make a table for this stream, c.s mul c posits, and we know that this is going to have, we need to find the 0th element, the first element, and actually that's all we need because we don't need to find the second element that would go here. And so let's make a table, and then we also know our const stream 2. We need to find the 0th element and the first element, and so we already know those will be 2. I'm going to erase this just so we have a little bit more room. 0th and first. So this combined stream needs to find the 0th elements of these 2 streams to compute the 0th element of the entire stream. So let's make a C and a posits here. There we go. Oh, that's a little messy, but that's okay. So we already know the 0th element of C is a 1. That's given to us. That's why it's actually not weird that we have a recursive sort of call to see here, because we're doing it element by element. That's a great thing about combined stream, is it only looks at the 0th element of both to calculate the element, and then looks further. So 1 is the 0th element. Posits we know is 1, and actually we know this is 2 as well. So let's calculate the element that would go here. We know that it's going to be adding, multiplying 1 and 1 with 2. So multiplying 1 and 1, which gives us 1. Adding 1 with 2, this would be 1, this would be 2. Adding those together will give us 3. So we know that this element's going to be 3. And then we actually can replace, we know now this the first element of C is going to be 3 as well. So now we can actually calculate the second element, which would go here, by multiplying the first elements of C and posits together, which gets us 6, and then adding that with 2. That gives us 8. All right, so it's not so bad if you do it element by element, and let's look at mapstream as well. So mapstream applies. So it's important to note that mapstream applies fn of s0, fn of s1. And actually what we can do here is we know that our function is a nested lambda x with a lambda y, which returns x times y. So our first fn call is going to return this lambda. And we actually know that that will happen for every element, because nested lambdas, if we call the first lambda with an element, we'll just get the second lambda returned. You have to actually call it with one more parameter or something like this, 7 or something, to actually evaluate the value here. So we know that our stream is actually just going to be a bunch of functions, because by definition, map stream right here, is going to be, map stream is going to be applying this function exactly like how I spelled it out here, returning this lambda over and over again. Okay, so let's look at D. D is combined stream with a function and applying it to A and posins.rest. So let's make a little table again. So we know that our combined stream, so let's make a table. We need the 0th elements, the first element and the second element of our substreams. So our substreams are going to be A and posins.rest. So we know posins.rest, we already know, is going to be 2, 3, 4. And then now we have to evaluate A. So let's look at what our first element of A is. Well, we know the first element of A is going to be the lambda x, lambda y, x times y on the posits itself. So we know that this element right here is going to be 1. Applying fn, well, we'll pass in 1 as x, and then we'll actually return a lambda of x times y. So actually our first element, I'm going to write it right here because I need room to put my face over here. So we know A, the first element, is going to be actually lambda y, x times y. So it's going to be a function, lambda x, y, x times y. So this is the 0th. Sorry, not first element, 0th element. I could have wrote it here. But it's important to note that this actually has access to an x value, which is 1. Because notice here, we passed an x value, which is 1 here, and this is like a higher order function where we got the lambda returned and we passed in 1 for x. So this is 1 times whatever y we pass in, which we don't know just yet. And then the same goes for our first element. Sorry, let me write it here. Okay, so our first element of A is a lambda with y, where x is actually 1 times y. Our second element, I keep using the wrong words. Sorry, our 0th element is lambda y, x times y. Our first element is lambda y. x times y. But just like the same logic here, we're actually going to be passing in a 2 times y. And same goes here, lambda y, 3 times y. All right, so now we can actually apply our lambda f x of x call. So, which is actually right here. So what we're going to do is we're going to apply this with each element of our table here. So our first element is going to be this lambda applied with 2. So we pass in 2 as y. We get 1 times 2 is 2. So we know actually our 0th element is going to be 2. Then we do the same thing here. We do 3 gets passed into here. 3, 2 times 3 is 6. Then same here. 4 times 3 is 12. I would definitely think a little bit more about this question. Definitely let it sink in. And I know my work is really, really messy over here. So please post a follow-up or something if you still are confused. Obviously, you can also put this in Python Tutor, and that will help as well. All right, let's move on to 1C. It looks like this is a what would scheme print. So before we run through the code, we actually look at our expression, and this has nothing to do with our code, so let's run through that. Remember that cons is sort of like our link constructor in Python, where it takes in an element, and then actually the rest has to be a link as well. So if we do something like this, this will actually get printed out as 4 with nothing, because the rest is a list, and so it'll just extrapolate the values from inside. The same goes with something like this. Does that make sense? Because this is equivalent of saying cons 4, cons 5 nil. The quote form just turns that into a cons 5 nil. So let's look at what quote form does. Or I guess it's pointing the other direction. Quote is like saying. Quote is like saying. It basically converts. What did I say? Well-formed, ill-formed lists to well-formed. And it's not so important that you know what well-formed, ill-formed means. It's more important that, sorry, we'll see what this means later. And what it actually does is it does not evaluate, besides converting well-formed, ill-formed list to well-formed. So let's loop through our elements. So what that means is that something like 0 dot parentheses, that is a ill-formed list because there's a period here, but it's actually well-formed because there's a 0 with a dot, but then the thing after the dot is actually a list. So it will get rid of the dot, get rid of our list, and then just output 0. The same goes for something like this, 3.4. 3.4 is going to cross out the dot, cross out the list outside, and output something like 3, 4. Because that's like drawing it out. That's like saying something like 3, and then the dot notation is saying, okay, so something after the rest is a value. Well, the value ends up being another list with 4. So we can write this like that. However, +1 is not any of these forms, so it does not get evaluated, so it just gets outputted. So our final list is going to look something like 4, and then what I was talking about earlier, where we get rid of the parentheses outside, so we actually get rid of that and get rid of that one, and get 0, 3, 4, and +1, 1, like that. All right, do I have enough room? Okay, I do have a little bit of room. So let's work through the code here and apply it. So before we get started, remember that moo is dynamically scoped, which means parent of frame is frame that called it. Unlike lambda, where parent is frame where it's defined. And lambdas actually are normally how Python works and how most of Scheme works, and so mu is just sort of a special case. There are languages that do implement dynamically scoped functions as well. So let's actually, it'll be really useful to draw an environment diagram for this. Although we don't teach you how to draw environment diagrams for Scheme, it's the same concept. So we make a global frame. We define a function, remember this is a function, f, that points to a func f, parent equals global. Then we have an h1 that points to a lambda, parent equals global. And then we have an h2 that points to a mu, parent equals question mark. Because we actually, as I was saying, dynamically scoped is the frame that called it. We did not call our mu yet, so we don't know what parent it is. The parent actually changes every time we call it. We know that the parent of our lambda is global because that's where it was defined. All right, so let's do h1. Or actually, rather, let's do this call right here. So this call is, we'll create a f frame, f1, f frame. It takes in three elements, g, x, y. G is going to point to h1. X is going to be 5, 11. All right, and our return value is going to be g of x. So g of x. So we create another frame, a lambda. Lambda takes in a. Oh, parent is global. That's important to note. Parent is global. Takes in an a. The a is 5, because we called it on 5. Then our return value is going to be right here, a plus x. Well, a is here, but x, we look in our global frame, or our parent frame, doesn't exist. It exists in our frame 1. But remember that our lambda was defined in parent global frame. So there is no x. There is no x. No x. No x. No x. And error saying, you know, variable x not found or whatnot. All right, so let's move on to this call. This call is whatever our f3 frame. It's our f, takes in g, x, y, and then our return value. G points to mu. Okay, I can draw an arrow. X points to 5, y points to 11. Then our return value is g of x, which is 5. So let's draw another frame, f4. This is our move procedure. So it takes in a y. Remember to bind your formal parameters. Y is 5. And then it returns right here, y plus x. Well, remember our parent is, oh, right, our parent now, well, what frame did we call our move procedure in? We called it in our f3 frame. So our parent is actually f3. So when we look for an x, we actually find an x here. So we do an x. So our y is in this frame, but our x is in this other frame. So it actually gets 10, which gets returned here, 10.
Hey everyone, my name is Raymond, and I'll be starting this walkthrough on problem number 2. Here we're given 2 lists, where each list contains 3 elements. Notice how we have this pointer here. That means the second list is nested into the second element of the first list. So since we're given 4 lines, we can separate each line with an arrow. So let's construct the initial list. That's this. So we have 1 here and a 2. So notice that these could be anything. We can just give them none. So L starts off as none, 1, and since the second list is nested, the second element of the first list will have none, 2, none. So we have 3 lines here, and for each one of these lines, we're going to change one of the nones to an arrow and reference it to the correct object. So let's first change the 0th element of the first list. It's going to be pointing to the inner list, so that's L of 2. Now, to get this element, is going to be the 0th element the second element of L. And here we just want to reference it back to L. And same thing for the second element of the inner list. And let's reference it back to L. All right, in question B, we want to construct the above sequence with tuples rather than Python lists. So we can consider a scenario. So let's say we created our sequence, both the outer and the inner list first. Well, since tuples are immutable, there's no way we can change these three values. Right. The other thing that we could try is we can compute this first and then create the second tuple and have these point all the way back to the beginning. But again, we can't add this or this because it's a tuple and again it's immutable. So the answer is no. Moving along to question 2C. Here we're given an environment diagram that's already drawn out for you, and we're going to write the code to replicate the diagram. So the main important thing is we see that the program is about to call print hello. And we have three functions where each one is parent is from another frame. So here we see that we're defining G in F and defining H in G. So the first def is going to be our F function, the second one is going to be the G, and the third one is going to be at H. So since we're going to call print hello, so we haven't called print hello yet, and we see that H has no return value, so the body of H is just going to be print hello. Right. So next we're going to let's look at the code following our def statements. We have func as creating a list with two elements where they both start off as none. But here, the first element is pointing to G, and the second element is going to be at H. So with an F, we want to mutate func, 0th element, to be G. And within G, we want to mutate func's first element into H. And we can only do it in these respective lines because we want to return 0 in F and return 1 in G. And since H is defined in G, we can only mutate func of 1 in G. Right, same thing goes for F. Since G is defined in F, we can only mutate func of 0 in F. So here, within G, we just want to return 1 and return 0.
All right, so let's take a look at 3A. So this looks like it has to do with dictionaries. It looks like a writing fill-in-the-blank Python code. So let's look at what they define for us. So they say a nested dictionary is when the values themselves are dictionaries. So notice how A maps to a dictionary B, which has the, not dictionary B, a dictionary that has the key B that maps to dictionary that has C, etc. So they tell us that to flatten it, we basically take the keys and then map it to the deepest value. So ABC would be 1, ABD would be 3, and and A and C would be 2, etc. So this is sort of like our flattened linked list question we've seen previously, where let's just say our first element is link, whatever, and we only want to call our flatten link if our first is a link. So we have something like that in our function here, except now we have to create a new dictionary that we return. We have to loop through our dictionary items, and then this is exactly what I was talking about. If it is an instance of the dictionary, we call our leap of faith, flatten dict, v this time, and then but unlike our linked flatten question, we're going to have to actually loop through our flattened dictionary to put it into our new dictionary. So for k0, v0 in flattened dot items, then we add it to our new dict, and then we don't know what our key is yet. But remember, this is how you add to a dictionary. It's also how you reassign in a dictionary, which is convenient. So v0. Okay, let's take our leap of faith and assume that flattened dict is going to return the flattened dictionary that we want. So the key values would be B and C and B and D. So to get the key value we want in our final dictionary, we need to add an A in front of there. So what do we need to do here? Well, our key, at least in this first part, is our key is K, and our V is now flattened. We have to say K plus underscore plus K0 equals V0. And we're done with the is instance part. So if it's not a dict, then all we need to do is add it to new dict. Add our key and our value. All right, so let's look at 3b. A polynomial can be defined as that. Hopefully you're familiar with that. It can also be listed as coefficients, and then we can take out the x and break it into multiplications, like all this confusing stuff. Luckily, they gave us an example. So 3x cubed plus 2x squared plus 4x plus 1. Notice how we can take the 3, multiply it by x, add the 2, then multiply that whole value by x, add the 4, then multiply that whole value by x, then add the 1. So if we look at our code that we have to write, oh, notice how they actually import reduce for us. That might become helpful, especially because we only have one line to write it. And I'll review what reduce does in a little bit. So we take in a list 1, 2, 3. So we know that we're going to have to do 1 times 2 plus 2, multiply that whole thing by 2 plus 3. So this is 4 times 2, 8 plus 3 is indeed 11. Okay, let's review what reduce does. Well, reduce is one of those built-in list functions. If we take reduce, we pass in a list. Or actually, rather, I think we pass in a function first. So let's make a lambda. This function has to take in two values, x and y, and let's just multiply them together. And then we pass in a list, 1, 2, 3. So what reduce does is if we draw boxes, it's easier to visualize this as a tree. We draw boxes for our 1, our 2, and our 3 for our values. Reduce will apply our function to both of these, apply function, where this becomes x and y. So this is x and y. It'll apply our function. It'll spit out a value. In our case, we're going to multiply them. So it'll spit out to 2. Then we're going to apply our function again to 2 and 3, and then multiply them together to get 6. So notice how that sounds very familiar, very similar to what I was saying before, where we have to, multiply our x by 1, add it to our next value. So in our case, multiply 1 by 2, add it to 2. Then do that same thing again, get that resulting value, which in our case is right here, multiply it by 2, then add this value right here. And so that's actually our solution. We write reduce, we write lambda, takes in x, y, and then instead of multiplying them together like what we did here, we actually want to multiply our x. Uh-oh, wait, we already have an x here, so let's call them something else. A, b, let's multiply our a by x, then we add our b, and that'll do it for every single, so it'll take these two, multiply our first one by 2, add it to 2, then our resulting value is going to be our a here. My bad, I should have used a and b over here. And then we actually pass in our coef. And that's actually our solution.
All right, moving to question 3c, we want to write an all equal. So given a linked list and a list, we want to make sure that they're equal, not in elements as terms in the value, but also at the depth, right? So both linked list and list can have nested linked lists and lists respectively. And so here's an example where we have 3 links where the first and the third one are nested linked lists, and the respective linked list would be lists with 3 elements. The 0th one is the nested list, and the second element is also a nested list. So here in the first true case, we see that we have this doc test. So when the linked list is empty and the list is also empty, then it must be true because they're the same. They have no elements, so they're the same list. Right? So what about the false case? So consider this linked list with this list. If we make the recursive call to the rest of the linked list and the rest of the elements besides 4, we're given a linked list with 5 and an empty linked list. So this is obviously not the same value with 5 and empty. So if one of the linked lists is longer or shorter, then it must be false. So if R is linked.empty or L is empty. And we don't have to worry about whether they're equal again because we already made that check up here. So next, we're going to look at deep linked lists. So if the first element of our linked list is another linked list, and that the first element of our list is a list, then we must check whether these nested lists are also equal. So in order to do that, we already have a function defined for us, which is actually the recursive function, all equal. We want to check whether r.first and the first element of L are equal. But after checking these, we also need to check the rest of the elements, right? So we have an n, all equal. The rest of the elements will be r.rest. And to pass in the list L, we're going to slice it from 1. Now, what if one of them is deep at the first position and the other one is not? So like in this case, this one is a 2, whereas here is a linked list. So obviously, we just want to return false because they cannot be equal if one is in value and the other one is another list or linked list. And finally, if the first elements are true, then we just want to call it equal. Well, actually, now we're looking at just 4 and 4, right? So we need to first check that, make sure r.first is equal to the element at the 0th element of L, and also make the recursive call on all equal to make sure that the rest of the elements are the same. So in this question, all we want to do is just, we want to fix errors, right? So look at the iterative version of PowerGen first. We see that we have if self.n is greater than 0, right? But nowhere in this the body of this if suite do we change self.n. So we're never going to reach an end. So what we should add is self.n. We're going to decrement it by 1. Next, we see that r is set to self.i. Right? Self.i gets updated to the next value, and we're returning self.i. So we'll never return 2, right? R is going to be set at 2. This gets self.i gets updated to 4, then we're returning 4. So rather, here we want to return r. And remember that iterators, unless they represent an infinite sequence, we need a stop iteration exception. So PowerGen is not an infinite sequence because we want to iterate until we reach 2 to the power of n. And so we have an else race stop iteration. Now we see this our iter return iterator, thus returning self. But also we want to see, is this, do we iterate through the sequences the number of times we want, right? Is it greater than 0 or greater than equal to 0? So let's make it check. So if self.n it starts at 2, we want to reach both 2 and 4, right? So this is greater than 0. We're going to output, we're going to reduce this by 1, output 2. And the next time we call next, we're going to reduce this by 0, output 4. Now that is 0, we're going to stop, right? So this is correct. Well, the other thing is self.n does not exist in it. So here we also want to add self.n is equal to n as an instance attribute. Right. Now let's look at the generator version. Again, we use n as a check, but we do not decrement it. So here n gets decremented by 1. And remember, since this is a generator, we cannot use return. This becomes yield of I. If we use return, then calling next on whatever power gen outputs is going to error.
All right, let's move on to question 4. So how old is the sun in galactic years?
18.4.
All right, so let's get started with 5a. Consider the sequence that's sort of like the Fibonacci, where we have 1, 1, 1, 3, 5, 9, 17, and they define it. So it's sort of like one of those problems on the first homework, like G or iter or something, where we look at the last 3 elements and we add them all up to get this one. So 3 is 1 plus 1 plus 1, 5 is 1 plus 1 plus 3, 1 plus 3 plus 5 is 9, etc. We can implement a function that finds the nth item of our sequence indexed at 0. This is actually pretty important. So our first element, 0, 1, 2, 1, 1, 1. Okay, but this implementation is not tail recursive. Can you see why it's not tail recursive? Because notice how, let's define tail recursive. Basically, tail recursive means that the last function that has to, or the function that's in tail context is the recursive call. So what's happening here is that the last function that gets evaluated is actually our plus. And so what that means is that when we create our frame, and then we call our recursive call, we get some value, and then our return value, we have to keep this frame open because our return value has to add them together, plus them together. Tail recursive is very efficient because what we can do is we can create a frame, and then once we're done with this frame, we can actually cross it out and then create another frame sort of on top of that frame, because all our values are going to be sort of kept tracked in our parameters. That'll make a little more sense later. And actually, you should review the discussion that talks about exactly what is in tail context, what isn't, and basically if the tail recursive call is in tail context, then the entire function is tail recursive. So how can we do that? Well, a neat trick is to use helper function, where we store values as params. And we'll see what I mean by that in a little bit. So actually, yeah. So we know that we're going to have to be keeping track of 3 numbers because we have n-1, n-2, and n-3. And so I'm going to call these values n1, n2, and n3. And actually, there was a problem like this on discussion where you have to write Fibonacci tail recursive. So hopefully this is not too foreign. But yeah, so let's not fill our base case yet, but let's actually write our tail recursive call. Remember, we can't have L plus or minus outside. Our final statement, if in our else case, is going to be our f tail call. So what are we going to do to k? Well, k is going to be sort of like an index, as we can see, because we're going to be passing in n-3 here. And that's just sort of like a feeling that we're going to have to keep track of what index we're on. So what do we do? Well, a neat trick is to use k as a counter and decrement it, which means that our if case is going to have to deal something with k and 0. But we don't know what yet, just yet. So what do we want to do to n1? Well, we move n1 to, so n1 is going to be that 1 here. Well, that 1 here is going to turn into that 3. That 1 here is going to turn into that 1. And that 1 here, let me erase all that. So this 1 here is going to turn into that 3. That 1 here is going to turn into this 1. And this 1 here is going to turn into that 1. So basically what we're doing is we're shifting. So we're shifting over. So our n1 becomes our new value, which is actually plus n1, n2, n3. Our n2 becomes, oops, why did I write a comma? Our n2 becomes n1, and our n3 becomes our n2. Okay, so let's put a equal symbol here. Just, once we hit 0, maybe that's when we want to stop. And what do we want to return? Well, we want to return n1, because n1 is sort of the value that's going to be getting updated every time. Okay, so let's go to our f function now. Notice how our f function is also tail recursive, because notice how it's calling a function that is tail recursive. So yeah, so we have a case if n is less than 3, we are hard code 1, but If not, then what do we want to pass in as n1, n2, n3 as our starting values for n1, n2, n3? 1, 1, and 1. All right, and so what you should always do when you do these code written questions is test out if it actually works. So let's try n equals 4. Okay, 4 here, we define ftail. 4 is not less than 3, so we go to our recursive call. We decrement 4 by 3, so we get 1. So k becomes 1. All 3 of these become 1. If k is 0, we'll return n1. Okay, it's not 0. Ftail, so now this will become 0. This value is going to be 3 and 1, 1. Well, k is 0, so now we return 3. Is that correct? Well, remember what I was talking about before. It's 0 indexed. So that means, sorry, this value should actually be 3. Then our 4 should actually be 5. So right now our code is giving us the wrong answer. It's giving us the prior value. So that means we actually have to change our base case to less than, because that means then once it hits 0, it'll still, so this is our k, it'll still be 0, but then it'll go to -1 here, and we return this value, which is what we want. So now our code is correct. All right, let's look at 5b. A stack is a sequence in which items are added and removed from one end, which is known as the top of the stack. So you can imagine this is like a stack of pancakes. So basically, we can either add to on top. So we add on top, add on top, we add on top, and we can only remove from the top. So we just add, remove, add right from the top. And this is actually a really useful data structure, and we'll see that a little bit more in like 61b. But so let's look at how we can simplify computation. So 5 plus 1 plus 2 times 4 plus 3. So they rewrite it as 5 plus, so 1 plus 2. So they do this part, 1 plus 2. Then they actually multiply that by 4 first. Remember PEMDAS PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. So we actually do that multiplication first. And I actually got caught up when I was doing this question because I didn't realize that. So we multiply it, and then we add 5 using this plus right here, and then we add 3 using this plus. All right, so let's look at our function. Oh, they say do not use pop, so that's important. Okay, so our compute postfix is going to take in tokens. It'll take in a list of exactly what we saw. It'll somehow output 20, because I guess that's the arithmetic, or the result of doing all our operations. It's going to create an instance of our class. It's going to loop through each symbol. If it hits symbol, or if it hits something, it'll do the operate. Well, that sort of indicates if it hits an operator, it should be doing something different than if it hit just a normal number. So we're going to say if symbol, and then remember, how can we check membership for a dictionary? We use in operators. Actually, I guess this would be all caps because they defined it like that. Operators. Then we want to do operate, else we want to push, and then at the very end we want to pop off our stack because we're going to be left with one operator. Okay, so let's walk through. What is one function that we always need in our classes? Well, we need an init method. Actually, that's not necessarily true because in init, all classes inherit from the object class, which has an init, but I think we'll need an init because actually I skipped a little bit part. We want to be using lists. That's key to implement this. So what do you think our init's going to have? Well, our init method's going to have a self.list to keep track of what numbers we have so far. So conceptually what's going to go on is we're going to have an empty list. We're going to add numbers to it. So first we'll add 5, then we'll add 1, then we'll add 2, and then once we get to a plus, we're going to do some special operate, which is somehow going to take these two numbers, apply the plus to them, apply, and then replace this with whatever that value is. So in our case, 3. And then continue moving on here. So then, our self.list is going to contain, 5 and then 3 after, doing our special operate method on it. So, okay, let's see, what's an easy function to implement? Notice there's only 2 lines here. Well, that seems to be our push method. Our push method is going to, remember all class functions take in self, and then it should take in a symbol, I guess, so sim. And what's that going to do? Well, it's just going to add our symbol to the end of our list, as I was just talking about. Okay, then what are we going to do here? Well, is this our pop method or is this our operate method? Well, our operate method, we know, is going to remove these 2 values and then add them together. So it's actually going to pop off these 2 values and add them together. So that seems like we could write it here or we could write it here, but it seems like we only need 2 lines for that, because we could say something like, so this is going to be our operate. It takes in, again, a self and a symbol. And then we want to say we're going to pop off, so x and y are going to be popping off self.list. Oh wait, not self.list, sorry. Self.pop, comma, self.pop. And then what are we going to do? Well, we're going to push the result of self.push, the result of applying our function, so operators, operators, bracket, remember this is a dictionary with our sim, because we already know that our symbol is in our operators because we checked for membership right here, and then push, and we're going to apply that with our x and y. Does that make sense? So conceptually I was thinking is that we're going to add the 1 and 2, then we're going to pop off both of them using a pop method that we're going to define later. And we just take that sort of leap of faith that our pop method is going to remove our 1 and 2, then we apply our plus to it. And then add that back onto our list. Yeah, so now we have to do pop. Pop takes in only self. And so what do you think pop does? Well, pop, imagine we have a list, 5, 1, 2. We want to pop off this element. We can't just say self.list.pop. They told us not to do that in the beginning. But another way we can remove elements is using del. And actually, we can use dot remove as well. But we'll see why this doesn't work in a little bit. So del, the syntax is del, and then list, and then the index. So we wanted to be deleting the last element. How can we get the last element? Well, we could use len, or we could use -1. Remember that -1 will get the last element. So we could write that here. But you can't write x equals del, because del doesn't return a value, it just deletes the value. So what we need to do is we actually have to save the last value into a variable and say self.list -1. And then we can say del self.list parentheses -1. And then what we can do is now we want to, what do we want to do after we pop it? We want to return it, right? We want to return x. And we also need to keep track of that. Okay, so you might be thinking, why can't we use remove? Well, remove checks for the first instance of, sorry, that's hard to read. This is a 1, not an L. First instance of the element that you remove. So we can't use this because it just so happens there could be a 2 here. And so remove will actually remove this 2 and not this 2. But yeah, so this is the solution.
Next, for question 5C, we're going to be analyzing worst case time complexity. Notice that given multiple inputs, we want to use the respective inputs in our big theta notation. Right, so let's look at the first, let's look at A. Here, I starts off at 0, 1, 2, all the way until m. In each iteration, J starts off at 0, 1, 2, all the way until n over 100. Now, this is a constant, and since we're incrementing by 1 every time until we reach this, this is actually still just theta of n this is actually, so the number of operations that we have. So number of operations is n over 100. Remember, we take out constants, so theta is n. So each one of these would be theta of n. Runtime, and since we have m of these, total runtime would be m times n. All right. Next, look at B. Here, our two for loops are separated. They're no longer nested. So I goes from 0, 1, 2, all the way until m over 3. J goes from 0, 1, 2, 3, all the way until n times 5. So both prints are constant time. So the number of operations we have would be m floor divided by 3 plus 5n. Remember, again, in big theta notation, we're going to take out both constants. So our theta is just going to be m plus n. Now we have D. So let's analyze again. The outer for loop, I goes for 0, 1, 2, 3, all the way until m. Right. But now j starts with 0, and we're going to increment j until we reach I. However, j gets updated by 100 every single time. So here, so what's going to happen is that from 0 all the way until 100, j is just going to start off as 0, right? It's going to reach 100 and it's going to stop. 0 to 100 and it's going to stop. All the way until 100. 0, 100, it's going to stop. But at 101, 0 is going to go to 100, then 200 and stop, all the way until 200. And again, this goes until 300, and here it'll be 0, 100, 200, 300, and all the way until m. So at m, the number of operations that we have is actually just going to be m over 100, because j increments by 100 every iteration. So since we have m of these operations, well, these, in the worst case, this number of operations here is going to be theta of m. So it doesn't actually matter what these smaller iterations of j's are, because this one still dominates. So our final runtime is going to be m squared. Now, for f, we only going to have one argument here. Oh yeah, also back for D, since n was never used here, and it's not mentioned in our runtime. So for m, we're going to start I as 1. I is going to get multiplied by 2 until we reach m, right? So I is now 2. In the next iteration, this gets updated to 4, 8, 16, all the way until m. So this is actually really similar to another runtime, whereas let's say I start off as some value n. It gets decremented by a half, so n over 2, and then this gets decremented by half again, all the way until 16, 8, 4, 2, 1, right? So this is what we call log n. And here, this is just the reverse of this, the n from going from n to 1. This is just going from 1 to m. So therefore, this is just going to be a log of m. So moving on to the last question of this final, given a stream, we want to output another stream that contains the increasing subsequence of the initial stream. So let's look at this example that was given. Rather than getting 2, 3, 5, 6, we want to start off from 10 and just find the increasing subsequence from 10 onwards. Right? So initially we had 10, 2, 3, 5, 26, and onwards. We're looking at 10 and 2. So 10 is in our increasing subsequence, but 2 is not. So what we want to do is we want to give this a new stream back into increasing subsequence, but now with 2 taken away. So since the rest of a stream is always computed with a lambda function, all we need to do is just take 10 and it's going to be 3. So whatever function is used to compute 3 will be used in this new stream that's passing into increasing subsequence. So we're going to get 10, 3, 5, 20, and onwards. Again, 3 and 10 does not work. We're going to go take 3 out of it. So 10, 5, 20, nope, and 10, 20, 6. So finally, we see that 20 is larger than 10. Now we want to put 10 in there and also put 20 in there. But the rest, so everything after 10, we also want the increasing subsequence, but now we're going to keep 20 as well. So what we're going to do is just make the recursive call to longest subsequence to compute the rest of these values. So if s dot first is less than or equal to s dot rest dot first, so we're in this case, we want to keep the first value in a new stream. Oh, sorry, it's not this case. So if s dot first is less than or equal to s dot rest dot first, we're going to be in this case. We're going to keep the first value of the stream that we're going to return, right? But now in our compute rest, what we're going to do is, because we don't actually know that this is an increasing subsequence, we're going to make a recursive call that returns the stream, which longest subsequence, increasing subsequence does. And the stream that we're going to pass in is just going to be s dot rest, which is from here onwards. Now, back to these examples where we don't want the next value in our initial stream, we're going to make a increasing subsequence call where the first value of the new stream is going to be passed in is going to be s dot first, because we want to keep using this value to keep using 10 to make the comparisons. But now in the lambda, rather than get 2, we want a function that can compute 3 for us, right? So s dot rest is going to give us 2, but what we want is actually s dot rest to get this next element in 3. And with this concludes the video walkthrough for Spring 2014 Final.